Generative AI in software engineering has evolved from passive code completion utilities into autonomous agents capable of executing complex engineering tasks across the file system. However, these agents suffer from a blank slate problem. Every time a developer initiates a new terminal session, the large language model possesses zero knowledge of the preceding hours or days of project work. This forces developers to repeatedly re-explain project topologies and coding conventions, which directly reduces engineering velocity. This persistent amnesia is caused by the physical limits of the transformer attention mechanism, which processes data with an O(n)² quadratic computational complexity. This graph illustrates the scaling challenge. The linear O(n) line remains manageable, but the transformer's quadratic curve requires sharply rising compute as the context window expands. In long coding sessions, raw tool outputs bloat this window. The result is a significant increase in both token burn rates and compute latency. As the context window reaches its limit, the lost in the middle phenomenon occurs. The model begins to ignore instructions or hallucinate facts buried deep within the transcript. The the.mac/Claude Mem repository uses an architectural bypass to circumvent this bottleneck. It utilizes an asynchronous lifecycle hook framework and a memory system inspired by human cognitive tiers. Shifting the agent's data footprint from quadratic toward linear scaling allows the system to maintain project awareness across weeks of discontinuous sessions. Effective persistent memory requires the system to decouple semantic compression from the user-facing interaction. If processing happened in the primary thread, the terminal would freeze during every calculation. A simple grep search or a large compiler stack trace can generate hundreds of lines of raw text that must be processed. Claude Mem solves this by using lifecycle hooks to separate the developer's workflow from the background summarization tasks. This flowchart shows the architectural divide between foreground and background. The session start hook injects a compressed index in under 10 milliseconds. Then, post-tool use intercepts tool outputs, offloading raw data to the background process, keeping the main terminal thread completely unblocked. A bun-managed worker then processes these observations sequentially. It uses secondary API calls to summarize the data, while maintaining a system RAM footprint between 100 and 200 megabytes. This decoupling ensures the developer experiences no terminal lockup while the AI conducts architectural analysis in the background. Unstructured text dumps, like typical Markdown file inclusions, often lead to context dilution. As the file grows, the model's adherence to instructions begins to decay. To maintain precision, Claude Mem forces the summarization engine to output data into a rigid TypeScript schema. Memories are classified into specific types, like bug fix. Once structured, this information is routed into a hybrid storage layer for speed and conceptual relevance. A local SQLite database uses the FTS5 extension to handle deterministic keyword searches. This is where the agent finds exact function names or specific error codes. Simultaneously, a Chroma vector database stores mathematical embeddings of these narratives. This enables semantic search, allowing the agent to retrieve context based on conceptual intent rather than exact string matches. Managing two distinct database engines introduces technical friction. Bug reports have identified instances where vector relevance ordering failed, effectively degrading semantic search into a chronological log. To ensure resilience, the architecture includes automatic fallbacks. If the vector database is unresponsive, the system automatically downgrades to basic keyword searches within SQLite. This combination of strict typing and hybrid search allows the agent to query its history without overwhelming its active context window. To further mitigate the O(n)² scaling trap, Claude Mem introduces an experimental architectural workaround called endless mode. Endless mode partitions memory into short-term and long-term tiers. Instead of allowing tool outputs to accumulate in the context window, it replaces transcripts with dense summaries. The massive uncompressed data is moved out and stored perfectly on the local disk. If the agent requires the raw data later, it autonomously executes a query against the archive to pull that specific information back into its working memory. Maintaining a linear context footprint allows the agent to execute autonomous behaviors through an integrated skill ecosystem. The Make Plan v2 and Do v2 skills enable the agent to generate persistent implementation roadmaps and deploy specialized sub-agents to complete specific tasks. Because the memory is persistent, the agent can run anti-pattern checks, verifying current code against mistakes recorded in previous sessions. This two-tier architecture allows an agent to manage complex engineering loops that span days or weeks of work without suffering from contextual dilution. Establishing a persistent memory massively broadens an application's privacy surface area. Because the system monitors terminal logs and file reads, it naturally captures proprietary source code, internal discussions, and potentially hard-coded credentials. The primary defense is a local first guarantee. All indices, logs, and schemas are stored exclusively on the user's machine, with no unauthorized cloud telemetry. This table highlights the configuration surface available to the developer, providing granular control over how the system behaves. The Claude Mem mode variable allows the user to change the background worker's summarization style, prioritizing either architectural discovery or functional code changes. For sensitive data, developers can use the private tag. This instructs the worker to strip specific code blocks before they are logged to the database. However, achieving absolute sanitization in LLM pipelines is difficult. Edge cases in prompt handling can still lead to tag data leaking into the local persistent store. Automated pipelines also face the risk of recursive prompting. If the system captures its own meta instructions and feeds them back into the summarization loop, it can trigger an exponential token explosion. Despite these challenges at the edge of the context window, solving this statefulness bottleneck provides a persistent infrastructure layer for the next generation of autonomous engineering.